In this video, we'll talk about partial fraction decomposition with repeated linear factors. So I have a couple examples for us to work through here. Let's check out this first example. We have 6x minus 11 over x minus 1 squared. So we say that this x minus 1 right here is a linear factor, and we say that it's repeated because it's raised to a power of 2 or greater. So how can we decompose this fraction? Or in other words, how can we figure out what fractions were added together to get this fraction as the final result? Well, the form that we use is some constant a over, now first we write the actual linear factor itself, x minus 1. And then we say we add another constant b with the linear factor raised to the power of 2. Now, if this was raised to, let's say, the power of 3, then we would also have some other term out here that would also be raised to the power of 3. So we just write the number of fractions will just correspond to the power that this is raised to here. So we have a over x minus 1 plus b over x minus 1 squared. So where do we go from here? Well, we want to try to get rid of all of these denominators. So the way that we can do that is we can multiply this entire expression by the common denominator, which would be x minus 1 squared. So you can see that these three denominators, the common denominator among them would be x minus 1 squared. So if we do that, when we multiply this fraction by x minus 1 squared, the denominator will go away and we'll be left with 6x minus 11 is equal to, when we multiply this fraction by x minus 1 squared, we can see that we would just be left with an a times x minus 1. And when we multiply this fraction by x minus 1 squared, this x minus 1 squared goes away, and we're left with b. So now we just need to figure out how can we solve for a and b. Well, it helps if we first distribute this a into these parentheses. So let's write it like this. 6x minus 11 is equal to ax minus a plus b. Now what we want to do is we want to look for the x's on the left-hand side that correspond to any terms with x's on the right-hand side. And we can see that there's only one, so we would say that 6 must be equal to a. So let's write that. 6 is equal to a. And then we know that the constants on the left-hand side must be equal to the constants on the right-hand side, so that's negative a plus b. So we can write negative 11 is equal to negative a plus b. So we want to solve for a and b. So a is equal to 6. So we already know what a is. If we plug in a 6 right here, we would get negative 11 is equal to negative 6 plus b. To solve for b, we can add a 6 to both sides, so we get negative 5 is equal to b. So we've now solved for a and b. So our final solution can be written like this. A over x minus 1, we found a to be 6. So 6 over x minus 1 plus b over x minus 1 squared. We just found that b is negative 5. So we'll say negative 5 over x minus 1 squared. And that will be our final answer. So that is how we can decompose this original fraction into two smaller fractions. All right, let's try one more example. Let's say we have x squared plus 2x plus 7 divided by x times x plus 1 squared. So once again, notice that we have a linear factor in the denominator that is repeated, or in other words, it's raised to a power of 2 or greater. So how can we decompose this fraction? Well, the form that we'll use, once again, is some constant a. The denominator will be this first linear factor, x. And then we'll say plus some constant b over, remember again, when we have a linear factor that's repeated, the denominator of this first fraction is just going to be the linear factor itself. So just x plus 1. And then the last term will have some constant c over the linear factor raised to the power of 2. So x plus 1 squared. So once again, how can we get rid of all of these denominators to make this equation a little easier to work with? Well, we want to multiply the whole thing by the common denominator. So the common denominator among all four of these denominators would be x times x plus 1 squared. So when we multiply this first fraction by this common denominator, notice that this whole denominator will cancel out. And so we'll be left with x squared plus 2x plus 7 is equal to, now when we multiply a over x by this expression, notice that the x's will cancel out and we'll be left with a times x plus 1 squared. Then when we multiply this fraction by the common denominator, we'll be left with plus b. We have an x and an x plus 1. And then when we multiply this last fraction by the common denominator, notice that the x plus 1 squareds will cancel out and we'll just be left with this x. So we'll have plus c times x. Okay, so now once again we want to solve for a, b, and c. So before we do that, it helps if we can first FOIL out this x plus 1 squared. So let's write that over here. Let's say x plus 1 squared. Notice that that can be rewritten as x plus 1 times x plus 1. So if we FOIL this out, x times x is x squared plus x times 1, and then we'll have plus 1 times x, so that's plus 2x. And then plus 1 times 1 is 1. So we can rewrite this expression. Let's write it like this. X squared plus 2x plus 7 is equal to a times this FOILed out version of x plus 1 squared. Then we have plus bx times x plus 1 plus c of x. So next, let's distribute this a into these parentheses, and let's distribute this bx into these parentheses and see what we get. So x squared plus 2x plus 7 is equal to, we get ax squared plus 2a times x plus a. And then over here we have plus bx squared plus bx plus c of x. Okay, the next step is we want to collect all of the terms on the right-hand side that have the same x values. So, and we can set them equal to the same x values on the left-hand side. So notice that we have an ax squared right here, and we have a bx squared right here. So if we pulled out an x squared, we would have a plus b. Okay, now let's look for the terms that have an x raised to the first power. Well, here's a 2ax, a bx, and a cx. So if we pull an x out of all of those, we'll have plus x, we'll have 2a plus b plus c. And then our last term that we're left with is this a all by itself. So we'll say plus a. All right, so the trick is we want to set this a plus b equal to whatever coefficient matches the x squared on this left-hand side. Well, if we imagine this coefficient is just a 1, we would have, let's write it like this, a plus b is equal to 1. And then if we set this 2a plus b plus c equal to whatever the coefficient is for the x on the left-hand side, we can see that's a 2. So we can say 2a plus b plus c is equal to 2. And then lastly, we can set this a equal to whatever the constant term is on this side, which is 7. So we have a is equal to 7. So we can see that we have a system of equations right here where we need to solve for a, b, and c. So let's make a little room. Okay, so we have a is equal to 7, so we've already solved for a. Now if we plug in a 7 right here for a, we'll be able to solve for b. So we get 7 plus b is equal to 1. So to solve for b, we can subtract a 7 from both sides, and we'll get b is equal to -6. Okay, so we know the value of a, and we know the value of b, so now we can plug both of those values into this middle equation right here. So we have 2 times a, so 2 times 7, plus b, which we said was -6. Let's write -6. Plus c is equal to 2. Okay, so we get 2 times 7, that's 14, minus 6 is 8. So we have 8 plus c is equal to 2. And to solve for c, we can subtract an 8 from both sides. So we'll get c is equal to 2 minus 8, that's -6. So we've now solved for A, B, and C. So now we can plug in these final values that we just found into this decomposed fraction. So we have A over x, we found A to be 7, so 7 over x, plus B, we found is negative 6 over x plus 1, plus C, which we just found was also negative 6, over x plus 1 squared. And that is our final answer. So that is how we can decompose this original fraction into 3 smaller fractions.